So, okay friends, good morning to all of you. We are going to start today's session, the lecture number 4, and our speaker is ready. So, more or less. So, without wasting time, we'll come to the technical discussion on of this topic related to lecture 4. Thank you. So, sir.
Thank you so much. Thank you so much. In this first, good morning. Good morning. We have, oh no, you can also sit here. In the, could you sit here? Thank you so much, because otherwise you are so far. Thank you very much. The lecture of this first lecture, I would like to do. Oh, good morning. Oh, please. Was on local energy communities and our studies that includes direct transactions among prosumers, and in particular we focus on the scheduling, but I will try also to say something about intraday. And I just started with this figure. I don't know if you can see. These are, I mean, the idea there is an incentive now to try to implement markets in the distribution network. We have the wholesale market, electricity market, but we want to, I mean, there are some directives, so interest in order to include also a market at the distribution level, close to the final user, in order to improve the involvement in the electricity market also for the final users, and try to reduce the market power of the big companies or the big players, and so try to increase the competition and so reduce the price. So the idea for local markets is can be to reproduce the same schemes of the wholesale market. So you see here the typical structure of wholesale market with the producers and the consumers that provides these bids into this auction for producing or consuming, and the intersection of the two curves is the market price. But as a big problem is that every day all the consumers needs to provide their bids, they offer, and the final users has not the capability every day to understand what is the price that is in agreement with the benefits of the use of electricity, and has other things to do. And also the producers are the prosumers, so the final use, that they have just a photovoltaic panel, so they cannot be interacted in this, that is a job, no? And they have their job. And there is another scheme that is the so-called peer-to-peer. So there is a producer that sells to the customer, the consumer, and obviously each producer can feed different customers. Also, this replicated in the distribution level in the local market as a problem, as all the problems of the previous one, plus also the problems that each consumer needs to search for the producer, and the role producer-consumer during the day, they change, because if you have a photovoltaic solar panel, you are probably a producer in some hours of the day, in the central hours of the day, but probably in the evening you are a consumer, so they are changing the thing. So the local energy community has the idea to to overcome these barriers in the creation of the local market. So I will just start with this figure here. That is the typical framework for our, the final user. You have that there are the retailers, in general more than one retailer or just one, and the retailer buys the power from the wholesale market, here indicated as power exchange, and the retailer sells the power to the final customers. There may be also some customers that in some hours they produce, and therefore they are producers that are, let's say, selling or inject the power to the grid, and the retailers or somebody can provide some reward to the producer. This is the usual scheme without the community. So what is the role of the community here? Is that it is an organization of consumers and producers that are writing an agreement to share the power. So it is an agreement with the producer and consumers, so that the producers, the users that are injecting power in some hours can directly share their power inside the community to the customers. So the customers have the possibility to take some power from the community, and obviously the rest it is from the retailer. So all the customers keep their contract with the retailers, keep the availability to choose the retailer that they want, and it is not mandatory to have the same retailer in the community. They can join or not the community, so in the same network you may have different users that belongs to a community or outside the community, or even or to different communities. In general, the community is limited only to the users that are connected to the same feeder, or they are fed by the same high voltage, medium voltage transformer. This is for the regulation of Italy, but this is the general concept, because this is a local market, and you cannot have the consumers and producers in different parts of the network. They need to belong to the same network. Obviously, in the community there is a balance, so that the summation of the power that is injected is equal to the summation of the power that is absorbed by the final customers. I don't know if this, please let me know if there are some questions and so on. Till now, no. Hope that is enough clear. Yeah.
So these blue lines,
Yeah.
they indicate basically it is utility related.
Yes, we can say the retailer, the utility. So you can say that you have a single meter in the house, and of course this meter measures some energy. We can say power because it is in the slot, no? So we can say power, and if you are outside the community, you have just this power to the grid. I mean, all the power is coming from the retailer, so you need to pay this. If you are part of the community, this part is paid according to the rules internal of the community that we need to a little bit to investigate now, and so this power is discounted by your measurement. And so you pay only the rest, I mean, the compensation, in order to take the power of the meter. Obviously, this is a calculation that is made post, no? Because you measure, and then when they are the billing, the community communicates to the billing system, that is the distribution system operator in Italy, communicates the balance of what is the injection and absorption of the customers, and needs to be balanced. So, and then for each customer, the bill is discounted by the amount that is relevant to the community, and for the rest, P-grid is paid to the reseller. Is a little bit clear?
Yes.
Yeah. So this is very important. This balancing equation, and we will use this balancing equation to put a price in the internal transaction. The price of the internal transaction is an open question, an open issue. I mean, it is not in general written by the law or the public regulations. It is in the contract of the community. So the community can choose different options. There are several options, and I will just illustrate the simple option to use this balancing constraint in order to fix the price of the internal transaction for each time. So this is a kind of dynamic price, because it can change, or it will change during the day, because in some hours of the day there is a lot of production internal of the community, so probably the price is low, and there are some hours in which the internal production is very low. So the price is fixed by the retailer. So with this introduction, that probably I can skip some or go through very fast with these slides, because they repeat what I have tried to say. The members of the community are connected to the same distribution network. The community does not involve resellers. Obviously, they are competing, let's say, with the resellers, leaving members free to choose their reseller contracts. The community reduces the interaction between members and resellers. We hope so. And the management system defines the transactions between the members of the community, so the community needs to have some management, and in order to improve also to exploit the possibility for this energy community to provide some energy at a lower price, probably also this balancing needs to be improved. So in general, community are installing some storage facility in order to improve the balancing into the system. And I mentioned this PLEC, that are the internal transaction. Obviously, when you have a meter and you absorb both the absorption or the consumption from the resellers and from the community needs to have the same sign. So you are consuming or are producing. You cannot have the P-grid, the power with the reseller, and the power with the community with a different sign, because it means that you are reselling the power of one of the two to the other. So both needs to have the sign. So this is the idea. And the community manager assigns the complement different between the measured quantity and the PLEC to the quantity P-grid assigned to the exchange with the reseller. Role of the incentives. In Italy, this discount of the bills is not in operation until now, although it is written in the regulation of the Europe. The implementation, first implementation in Italy, in order to push, to incentivize the creation of this energy community, is to provide an incentives without an impact to the resellers, so without reducing the reseller. The state of Italy, they provide some incentives according to the energy that is balanced in all the energy community, obviously the energy community needs to follow some regulation. For example, the production needs to be from renewables or in this way. The incentive is based on the energy shared among the members of the community. Specific rules limits the incentives to the energy produced by plants with a predefined characteristic and deny the use of storage system to virtually multiply the production. The model financed by public funds or bills is sustainable only for a limited initial period. So this is a transient period just to start these communities as long as resources allow. There are some peculiar aspects, a typical problem, the pricing of an internal transaction between community members, and the solution that we have implemented, the simple scheme. It is use the shadow price associated with the balance constraint that the sum of PLEC and PGrid is equal to the measured value. The formation of communities is favored when there is a distinction between distributed system operators and retailers, as in Italy, in which the distribution system operation cannot be a reseller. Balancing within the community allows a reduction in the need for grid expansion. This is expected. Yeah, I will go directly in this with the mathematical model because I need yes, we can also think about using also reactive power. At least in medium voltage level, there are users that often operates a low power factor, because if you have for example, internal generator in your system, and this internal generators produce power factor 1, so no reactive power, you reduce the consumption of active power, but the consumption of reactive power remains the same. So in some hours, you may operate a very low power factor, and in medium voltage, the customers connected to medium voltage, at least in Europe, they need to pay a penalty if they are consuming a very low power factor. 0.9 is the limit. So if you consume at a lower level, you need to pay a penalty. So we can think about also to have a direct transaction of reactive power. Since these customers are very close together, they can help each other in order to maintain a global power factor a little bit increased, and reduce the penalties. But I would like to go to the point of the model, and the last point is that these communities can also operate as aggregators, because they are, managing, operating several things, so they may also provide some ancillary services to the grid that can be used for congestion management, for example, for the distribution network. Obviously, it is important, the monitoring and management aspect. I have here a figure for this, but I would like to skip a little bit some figure in order to keep to try to answer to the question of the shadow price. So I'm going to this model here, and optimization model. We will see also another one with the incentives. This is without incentives. So this is the model for each community, or one of the models that can be implemented. But in general, they have this idea behind. There is an objective function that we want to minimize. Obviously, there is a summation for all the time during the day. This is the head optimization, and then we can also do for the intraday, and then the summation of all the users. Here it is also introduced this, that is the low power factor penalization that we want to minimize, but this is a detail. The important thing is that we want to minimize the cost of using some resources, distribution distributed generation inside, and obviously we want to minimize this, that is the cost of taking power from the retailer. So this cost is greater than the price. No, it is defined by the price that you need to pay to the grid, and if you inject power to the network, this power here becomes negative, and you will receive some compensation from the network. Obviously, this pi cell, it is in general much lower than P buy, so it is not much convenient. Otherwise, the community is not so important. But in general, pi cell is much lower than pi buy. And we can also include this that can be seen as a service to the network in order to avoid congestion, but for the moment we can avoid this. So we focus on this, and then we need to put, you see that is a minimization, then we need to put some balancing, some constraints, and here I put the balancing constraint in evidence, so that the power that is measured in all the users needs to be balanced from the power from the grid and the power from the community. So this, obviously there is also the constraints that the summation of PLEC for all the users, also the reactive power, it is equal to 0, so there is a balancing inside the community. The idea of the shadow price is that when you have a problem, a linear problem, because this is a linear problem, and also we can include then the constraints for the internal generators and also the storage system. But it is a linear problem. When you have a linear problem, for each constraints, you have a multiplier, a Lagrangian multiplier. I mean, each minimization problem, linear minimization problem, can be translated in a dual maximization problem. So at each constraints, you can associate, and the solver in general calculates directly, also a Lagrangian multiplier at the solution. So the solution appears with a Lagrangian multiplier for each of the constraints. So we can take the dual value, so the Lagrangian multiplier multiplied by the parameters, and this is called the shadow price of this balancing. What is the shadow price? It is that taking the solution, so you have the solution, solve the problem, so this is balanced. And you make these constraints a little bit much harder, no? So you increase a little bit, it is a marginal price. So you increase a little bit the consumption of the users, no? So after this little bit increase of this, how much is increasing the objective function? This is the shadow price of this constraint. So you have a constraint, I cannot go behind this line, no? And if you make the constraints harder, no? So this our objective function is a little bit increased, no? How much is increased? It is the price of this constraint. If you are not at the constraints, there is no price, no? So you are internal. Good. Thank you. This is the typical idea. Obviously, there are other methods and other, but this appears to be the fair for the final users, because it is a balancing between the price to the grid and the price of the internal community, so the price of internal community are not completely separated from the price of the resellers. If all the price are increased, probably also the price in the community needs to increase. But still there are some advantages. I will be back a little bit, and yeah, I'm on time. So we can go a little bit back in order not to avoid also these slides that says that the implementation, one of the aspects of the implementation of the energy community is that the energy community tends to exploit the availability in the market of some monitoring, because the energy community is very interested in monitoring all the things and all. So here there is a figure that of an actual measurement production in a PV panel. We have also installed these measurements into the local, the energy community. There are different types of metering, smart meter, that have also low, they use power line communication in order to transfer the data, and in general there are also devices that are called non-intrusive load monitoring that are available for the final use. This may facilitate all the things. And the other aspect that I would like to show to you is that we have tried in the laboratory to replicate what happens in the local energy community in order to understand how it works. So we have used a real-time simulator in which we have implemented the energy management system, so this optimization. And we have done two tests. One is taking directly the measurement from the final users, so the local energy community that I have also mentioned yesterday in Bologna. And we take these measurements and we represent in the real-time simulator the energy management system together with the model of a storage. In order to understand how the storage can be operated in order to maximize the benefits for the community. The other case is that the real-time simulators also includes the model, the representation of the community inside. There is also the reference. So these are the two systems that I've already described, and this is the optimization that we have implemented. This was a focus on the Italian regulation at present, so it does not include a reduction of the bills, a deduction of the bills, but includes the incentive. So this is the incentive that is provided by the public authority in Italy for the creation, at least the startup of these communities, and it provides an incentive side based on the energy that is shared. So this is the energy that is shared among the members of the communities for each time period. Was 1 hour and then 15 minutes. Just an example, 10 users, you see here the value of the power installing and the battery energy storage for 5 days. In these 5 days, they were on sunny days, the load is a little bit lower than the production, the solar production. This is the incentive that is according to the Italian regulation. We have also assumed that the resellers have a price that is above the wholesale price of this quantity. And the results of this optimization is that rolling optimization during the day Okay. It is that if there is no optimization, then there is this amount of energy. And with the optimization, you see that the energy that is purchased and also sold, it is increased. And this was unexpected because we think that we need to reduce. But it is also reduce the self-consumption. So many of the users, instead of providing power to themselves, they prefer to sell the power to the neighbor, no? And so on. So with this mechanism. But although this, in order to increase this shared energy according to incentives. So the incentive has this phenomenon that this self-consumption is reduced in order to increase the amount of the energy that is shared, because there are some benefits for this. So you see that not with the income and so on, you see that there is a decrease of total procurement costs of the electricity with respect to the case without optimization. I will be back again with another study that we have carried out also in collaboration with the distribution system operator, and there is this is a medium voltage network. It is in 15 kilovolt inside a city, so in urban area. You can see several feeders, but fed by the same substation, so the same medium, high voltage, medium voltage transformers. And we have taken this for winter days and summer days, 3 days, with the actual measurement recording of the consumption and production of all the customers and so on into the network. And we have grouped in the different communities in order to explore the effect of the presence of multiple communities in the same distribution network. In particular, we have considered 3 communities. We have just randomly assigned the nodes, the users, to the communities in all the days, in winter and summer, both for demand and generation. You see the share. So there is, for example, this community that in winter time and also in summer, but particularly in winter, has a low percentage of the total generation, and there is a community that is larger, and we have also considered the installation of battery energy storage, and this is the sharing of the battery energy storage among the energy communities, and in particular this too has a lot of storage. There are also users that are not included in the community. So in this way, we have implemented the optimization model that I've shown before, but I will show. Now, these are the profiles of the prices that we have considered. There are different tests. Now probably it's working. Oh, thank you so much. Good. We have considered also different resellers, no? So different, because each customer may have a contract with a different reseller. So we have considered a reseller with these profiles, that is the typical profile of the wholesale electricity market, and one profile in which there is price during the night. Okay. And then low price during the night but high price during the day, and another one that is a little bit cheaper from the other one, so 10% lower. But the maximum and the minimum are very similar, so but the different profiles.
So maybe there is an issue with the battery.
So the I've already described the objective function that is the summation of the cost. This power to
Hello.
level of price in the wholesale market. And in some days, not in all, but in several days, particularly, oh, thank you so much, particularly when it is a sunny day, in the middle of the day, there is a very lot of sun production from the sun. So in the electricity market, the price goes low. So they are replicating also this for the final users. But they are very rare. But we have implemented in order to see the difference. No? Is it reasonable? Oh, the model we put the minimization. This is the objective function for each of the community. So each community minimize this summation. This C grid can be also negative. When they are injecting to the network, they can also receive some reward. And I don't know if I can. Oh yeah. These are the balancing constraints that we have already seen. This is just the constraints that we have included in order to have the value of this QPF, that is the fact that the user is operating a low power factor, so there is a penalization, and this QPF is the reactive power that should be, it is considered as excessive, because it is an excessive consumption of reactive power, because the user is working at 0.7 power factor instead of 0.9. And this is calculated by this. So it is included in this. Obviously, the PLEC and QLEC are null for, and these are some of the results in this table. So these are just the costs in thousands of euros. So you can see the cost here. This line, these are the resellers, and these are the communities, winter days, summer days. And the first line is the cost for P-grid, so for the consumption from the reseller. And the second line, you see, it is PLEC, so it is the cost of the transaction, the internal transaction. They are negative or positive. Negative when globally, this group of users that belongs to Energy Community 1 and they have contract with the reseller 1 are injecting power. Positive when they are consuming power. You can see that the summation of the elements inside each communities, in the second row, it is perfectly balancing, because if one export users, the other group is consuming. So this is the effect. This table shows the comparison with respect to the case in which the communities are not implemented. So there are no possibility to direct transaction between the final users. So what are the advantages? And these are mentioned in percentage. You can see that the advantages are when you have no community, so the first row, and you see that in some cases, for example, winter, there is a 5% of reduction, 2% reduction, 5% reduction, 1% reduction. They are all different, no? So different users, they gain in a different way. So, but nobody is losing nothing. So no of the users in this way with this pricing mechanism has a disadvantage from the participation in the community. And this is important because in the community you cannot have, I mean, collect users that get a disadvantage when they are included, even though they don't have any solar panel or any storage system. No? This is just a table for the non-compliance of reactive power. So you see the big reduction when of these penalties when these transactions of reactive power are allowed. We have also done a test for a different number of communities, and the important thing is that the cost I mean, the reduction of the cost with respect to the case without energy communities, so the advantages are decreasing by increasing the number of communities. So the biggest, I mean, reduction of the cost we have when we have just one community in all the distribution networks. So the larger the community, the better. The idea, small communities, small local energy communities are in general not very important. So these are the details for the reactive power, and I mentioned that I have still some minutes, I think. So I mentioned that the energy community can also provide some flexibility service to the distribution network. In particular, the distribution system operator, we have this collaboration, was interested in see whether the energy community can provide some service for the voltage control to the network. So some capability in order to control the voltage in the network, so flexibility in terms of reactive power. We have considered both the flexibility up and down. So for Q down, the user decreases the consumption of reactive power. For Q up, increase the consumption of reactive power. Obviously, the distribution system operator is much interested on this. So in the reduction, the objective function that we have considered is the minimization of the cost of the energy with the resellers, and then this minimization, so with minus, so it is a maximization of the revenues for the provision of the reactive power flexibility to the distribution network. So this is the tariff that is allowed by the distribution system operator, and this is the maximum, it is the flexibility amount. And obviously this is down, so it is the reference profile minus the user, the actual user. For the app, you see that there is just the change here in the sign. So instead of decrease the consumption, you increase the consumption. In order to think about this implementation in the community, we have also allowed in the community the direct transaction of reactive power, and these are the details for the calculation of this margin for the low power factor operation. So this is the area of compliance. So when you are in the originally was green, here is a little bit yellow, and you are in this area, you don't pay any penalization, so it means that you are operating at a power factor above 0.9, and when you exceed this area, it means that violates the minimum low power factor, so there is a penalty from the distribution system operators. So this in the x-axis is the active power, in the y-axis there is the reactive power, that is the combination of the reactive power of the generator, the capacitor banks, if you have, also the reactive power provided by the battery, and the power, QLEC, that is the last one term here. It is the reactive power, direct exchange of reactive power among the users of the same energy community. So these are the equations that just represent this butterfly, I don't know, image, no, of these limits, and these are the constraints. So there is also the paper in which there are the details. We have put together both in order to calculate these margins, and you see here, this is for just one of the community, but day 1, day 2, day 3, the 3 days, and in red it is the, I need to see a little bit here, no. In black it is the reference profile of reactive power during the day. In blue, the maximum reactive power, and that you can increase the Q up. That is not much interesting. For the distribution network, it wants that you reduce in general the consumption of reactive power, but sometimes it happens. So it is the red one. So the red one, you have the margin. You see that in the first figure A, the margin, the Q down margin is very limited. This figure A is the results with the direct transaction of reactive power, QLEC. So if the reactive power capability of battery energy storage system or also distributed generation is used in order to reduce the penalties for low power factor operation, then the same resource cannot be offered to the distribution network as a flexibility for reactive power because they are already used this. The figure B is calculated without the internal reactive power, so prohibiting the reactive power QLEC, the reactive direct transaction of reactive power among the community. So you see that there is some flexibility in some times, no, that can be provided to the distribution system operator. So this is the global idea that when you provide service to the network, it means that these services, these capabilities are not used inside the community for the minimization, for example, in this case, of a low power factor operator. The more the resources are integrated in order to achieve a common objective, and the less these resources can be offered to the distribution system operator as a service for the network. They are the same. I don't know if you have any question. Probably this is the last slide for this. Do you have any questions so far? This is just a summary of some of these results. Scenario 0 with a community, including all the users, one community, and with the transaction of reactive power. Scenario 1 with a community, including all the users, but without the transaction of reactive power. And scenario 2 without the community. These are the summary of the results for Q up and Q down optimization in the 3 scenarios. And C-grid did the cost of the exchanges with the energy provider or resellers. And PNC is the non-compliance penalty. And R is the reward for the provision of flexibility to the distribution network. So you see that in all the scenarios here, for all these scenarios, you see that for scenario 0 and scenario 1, the cost of the provision of power from the retailers is the same. So the optimization, this direct transaction of reactive power does not have much influence on the consumption of active power, so in the costs for the resellers. But there is a clear indication for the penalty, because the penalty are 0 when you allow QLEC, and without QLEC there are penalties as in scenario 2. Obviously, in scenario 2, without community, the cost for consumption is larger than in the other cases. And these are for reference. And then for Q down, still there is the same effect on the active power, so there is no influence on the costs to the resellers, but there is some reward. And when you use the internal transaction in order to limit the penalties, the reward is very low, in this case 0, in this case is 0.7 for the summer day, this is for winter days. And when you don't have this internal transaction, the reward is higher, so it means that you can provide some service to the network. It is easier to provide service that increase reactive power by the users rather than provide the service that you reduce the consumption of reactive power. Any question? Any doubts? Is it reasonable?
One of the slides,
yeah,
you have shown that percentage of battery sharing.
Yeah.
So, say it is 14% or 30%, or that is the amount of energy shared by the battery for one particular day.
It is the fact that we have considered the case. We have added the battery because there are not much batteries into the system, so we have added in some places in which there is the photovoltaic units. We assume that the user that has installed several photovoltaic units, they can also install some batteries, so we have done this, and then we have assigned randomly the nodes to each community. So the percentage there are just the percentage of the total size of the batteries installed into the network that are assigned to nodes that are given to each community. For simplicity in this simulation, we have considered that all the users that are connected to the same medium voltage bus belongs to the same community. Obviously, this is just in order to simplify the model, but in general, from the same medium voltage bus, you have several users, and they may also participate in different communities. That was just to simplify the thing, because the data that we had were not for the single low voltage users, but where the data provided by the distribution system operators of the medium voltage bus. Total consumption. Any question?
Yeah, may I expect questions from your end? Any other questions?
Cool.
Okay. So thank you, Professor. So
Thank you to you.
we are concluding our session 4, and maybe a 5 minutes break. We'll take we'll start the session 5, but we'll start a break. It's only a break. So we'll just relax